Hello, this time I want to highlight a couple of shortcuts which work in some circuits that can allow you to determine the Thevenin or Norton equivalent networks much faster. Firstly, consider this network here. Now, I'm going to draw this in this way. I'll have a resistor here of R2, a whole load of stuff which corresponds to this current source, these two resistors, emerging down here, and then those two go across this voltage source here and out through R1 to A. And from there to B. Now, consider what the open circuit voltage would be. Well, the open circuit voltage is the voltage between A and B when there is nothing connected to the network. If there's nothing connecting to the network, then there will be no current flowing through R1. With no current flowing through R1, there will be no potential difference across R1, which means the voltage here would be the same as the voltage A. In other words, the voltage between A and B is just the voltage across V1. Our open circuit voltage is just V1. Now, what about the Thevenin equivalent resistance? If you don't have any dependent sources, which we don't here, we can determine the Thevenin equivalent resistance by setting all of the independent sources to 0. If I set this voltage source here to 0, then the network I would end up with would look like this. A resistor of R1 going through a short circuit, that just replaces the voltage source with a wire. Then we've got R2 going into something here and coming back out again. Well, the resistance between here and here is R1 in series with the parallel combination of this lot and a wire. But the resistance of anything in parallel with a wire is just 0. So our Thevenin equivalent resistance is just equal to R1. And since the Thevenin equivalent voltage is the open circuit voltage, we can derive our Thevenin equivalent network here just by examining V1, R1 and all of these components. The two current sources, resistors R2, R3 and R4, make no difference at all. And the reason for this is that they are in parallel with a voltage source. Anything in parallel with a voltage source isn't going to change the voltage between this point and this point. All it will do is change the amount of current that flows down through the voltage source. But they're not going to change the voltage between there and there. You could put anything at all on this side of this circuit, and the open circuit voltage would not change. It would just be equal to V1. And the resistance would not change. It would just be equal to R1. So we can get to the Thevenin equivalent network very quickly, just by ignoring all of this. Anything in parallel with a voltage source can be ignored. It's not going to change the voltage between those 2 points. A similar thing occurs for Norton's theorem when you have things in series with a current source. Consider this circuit here. Well, the short circuit current is just going to be I1 flowing directly out of A and back through B. It doesn't matter what you've got here. If you've got a current source and a resistance there, the short circuit current, the current flowing out of the output here and back into the input there, is just going to be equal to this current source I1, because this is a current divider. Since this has a zero impedance between A and B, all of this current is going to flow out of A and back through B. The short circuit current is going to be I1. But the short circuit current is just the current in the Norton equivalent network. Similarly, if we were working out what the resistance was, we would set all of our independent sources to 0. That involves setting this current source to 0, which means that no current flows through it. So no current is going to be flowing into this cloud of components because it can't flow back out again. We don't have a circuit. So we could just ignore all that part of the network and say that our Norton equivalent resistance is just going to be the value of this resistor here, R4. Anything in series with a current source doesn't change the current flowing in that part of the circuit. It's just determined by the current source. In the same way that anything in parallel with a voltage source doesn't change the voltage in that part of the circuit. Whatever is here does change the current flowing down through this voltage source, and whatever is here will change the voltage at this point in the circuit here. But in neither case does that have any effect on the open circuit voltage or the short circuit current coming out of the network. So we can ignore them. It's a useful trick to be aware of because it can simplify the production of equivalent networks in a lot of real practical cases. Next time we'll be looking at how to determine equivalent networks in the lab.